know what are the equations, how to solve it. So today, let's do a little different. Okay. So let me first present my entire screen. So is it visible now?
Yes, yes, sir.
Okay.
It's visible.
Is visible. Slides are changing.
Yes, yes,
It's
yes, yes,
visible.
yes.
Okay. So I welcome all the participants. So there are about 30 participants. So I believe uh, this session will be very useful. Unlike previous sessions, this will be mostly practical and industry oriented, which we will see how what is the effect of mesh size, how to capture the geometry, all those things I will discuss by sharing directly from the PowerPoint and the CFD and the software. Okay, so uh, the the topic which I selected here is simulation driven innovation. Of course, I will be covering this scale analysis and other stuff because little later on, because equations and analysis has already been covered a lot by the previous author. So let me start. See, one can stop me anytime in between to ask any question. Now, see the conventional method of production. I'm talking about see, there is a background sound. If you can, someone can mute your mic, then it will be easy for me to concentrate. Okay, thank you. So I am talking this CFD and or other methods in terms of industry, how industry uses this tool. Okay, you can see the process of getting a product till mass production. It starts with a design. Okay, it is maybe a 2D design or a 3D design. Then we make it prototypes. Okay, then after prototypes we go for testing, means to see whether the product is functioning as per the specification or not. Then in the testing, if there is any failure, then again go back to the design, again change the design, then make prototypes and again testing. So this loop continues, and this loop is a little longer in a sense because there is a lot of hit and trial done, and once your most of the failures are sorted out, we go for the mass production, which is the last stage for marketing and all other things. And see, today in modern method, what industry do is, again the first process remains same. If you see in the conventional method of production and the even the modern method, the design is the basic part. So where you need to design the part. Then the new step has come as CAE. CAE is nothing but we call it computer aided engineering. So any engineering, any new design, any new a product which we develop with the help of computers, this is called computer aided engineering. It's a general term. This is in computer aided engineering, it can be like finite element method, it can be a CFD or any 1D tool or 3D tool or any other method. Okay, then we do the simulation. If you see that there is some problem, if the stresses are high or the engine is overheating, you everything we decide at the CI level. And if there is certain changes need to be done, then you immediately go change the design, again come back, perform the simulations, and after certain level of confidence we get from the design changes, Then we go for the prototypes. Okay, now see, prototypes here also is there, and even in the modern days production or R&D, research and development, prototype is a must in a sense. You have still not yet got that much confidence on the CA that we can altogether eliminate the prototype. This is currently we are not at that stage. Of course, the number of prototypes in the modern method have come down drastically. So earlier it used to take, let's say, if you want to develop a, let's say, motorcycle or a mobile or a car or a truck. So prototype used to be in hundreds, and the cycle to market, it will take 2 years depending upon the product. But nowadays, since with the introduction of this CAE method, computer aided engineering, the cycle time for product development has come down drastically. So about, let's say, earlier it used to take 2 years, so now within a 12-month or 8 months, depending upon the product, one can launch the product in the market thanks to this CAE processes. It may be CFD, FEM, or anything like that. Then you go for prototypes. Then after prototype, you go for testing. And if again there is some failure in the testing, again you come back to the design and the process and go for the mass production. So this process is very fast. Okay, because most of the time we this process is fast in a sense. We have introduced, though we have introduced one additional process, CAE, but since this happens on virtual environment, so your product development has become really fast. Okay, so but it is really unfortunate in a sense. In academia, we don't give much emphasis on this process. Okay, you are still at the stage of like teaching our courses which we used to teach in 70s and 80s. And you see, even this the way the laptops, the computer have developed. Now you are getting the memory in GB, and the processes are in up to gigahertz. But the rate at which the computer have been developed, the same rate the courses have not been updated over the time. Still, it is the process of teaching. For example, we teach, let's say, strength of material, where we talk about bending and vibration. It's all theory. Students hardly get any exposure to model these processes, this theory, using computers, except couple of heavy lab work. They don't get proper exposure. But now that things are becoming so easy that those things also should be taught in a curriculum on a regular basis. It should be a core course rather than just mere electives. Okay, so I'll come back to those things. How so in future, maybe as a teacher, I see if I were the, let's say, a director of an institute, so I'll make compulsory, let's say, fluid mechanics and CFD together should be taught. So a faculty will have to improve and learn somehow. So it's not, so strength of material and fan element, it has to be go hand in hand, so that student can learn more on a design process rather than going through all coding and those stuff. Maybe a little bit can be taught, but the student should be allowed to more focus on the design and its interpretation. Okay, more and more on innovation level. They should think about the more new designs. And see, at the end of the day, one will appreciate that doesn't matter what we do perform, either CFD or FEM. At the end of the day, these methods will help us to take a decision based upon the analysis. Otherwise, if you cannot take a decision, the result has no meaning. In a sense, in industry, we perform all this analysis on the design, and and after that, seeing the result, you make a decision whether change the design or not, whether you can reduce the weight or not, or something like that. So similarly, students should be actually given more more focus on more thinking on the at the design level, creation of something new design and efficient design. Only then the innovation will come in our culture. Otherwise, theory, you see, in the age of this online teaching and and so much materials are available online. So unless we bring something new, design, interesting, which is uh, interesting to the students, things will not be easy for the teaching members, those who teach. Otherwise, nothing new, because theory and all things are available, and the lectures by Nobel laureates on these basic these processes and theory. So unless you bring something new, then the student will not appreciate. They think this is just simply as usual and boring, and they can get it, this information anywhere from online resources. Because I don't think so in future the norm will be only online. So unless we bring something new to the student, things will not improve. And see, so in the product design, you can see the initial phase of development. You can see the cost of changes. This is the cost of change. Even there is a small design change, the cost of change is not much. Okay, and at the same time, there is a lot of possibilities to make new design alternatives. So cost is less, and you have a lot of freedom to change. But as long as you move along the development phase over a period of time, what happened is the cost of change becomes more and more, whereas the number of design freedoms ultimately becomes less and less. Okay, so at later stages of development, I have seen myself in industry, it's really become tricky when we change even a minor design, because we have already process is set up, die is set up, order is already given for different product. So if you change one design, then the whole design has to be relooked, and it's a highly costly process. So initially, this phase, your CIE or computer methods comes really handy. In a sense, you can simulate a lot of design changes without incurring much cost. And based on this decision, you can make better changes initially in the design. But fortunately, in academia, as I said, not focus is given much on this. Hardly we remain bounded with some age-old theories, and I will never discuss on the design level. Okay, so I will not go into much into those. Since now, see, in the CFD, what we need to do CFD is we need to have a CAD model, as I said in the first design. So design is a must. Doesn't matter how we design. Okay. So CAD is a must. Okay. Then after CAD, we do the meshing. I'll cover most of the lectures in today's lecture is on mesh generation. Okay, because this from the CAD to mesh generation, it takes about 80% of the time, total time of the simulation. Okay, for real world problems, practical problems, mesh generation is not that easy. Okay, and it takes a lot of time. And after that, applying, taking suitable models and boundary condition, it's only 20% of the time. And of course, after that, it is some interpretation on the result. So since it is our mesh and pre-processing part, it takes 80%. So I will be discussing how we should generate mesh in a proper way, and what we should do and what we should not do. Okay, so those who are the beginners, so for them, so let me explain why we do the meshing. Okay, so if you don't mesh, it's a surface. So basically, it is having a infinite number of points. Okay, and degree of freedom actually we use in a sense of finite element. But even in let's say in CFD, so degree of freedom means the number of unknowns we solve. Okay, so unknown, for example, we are solving, let's say, only a fluid problem in a pipe. So the unknown will be the u velocity, v velocity, and the third component velocity and the pressure. So there are 4 unknowns. So there will be 4 equations or 4 degree of freedom. That you can understand that way. So here why I've written S6 is because the same stuff I teach for finite element method also. So per node there can be 6 unknowns or deflections in 6 direction. So the unknowns is 6. So if you multiply infinity by 6, it's a infinity. So and you have to solve infinite number of equations, which is virtually not possible. Okay. So when you mesh it, okay, so we actually create these nodes. Okay, and these nodes are finite because you're breaking this entire surface into small domains, finite volumes or element. And if you multiply the degree of freedom, you have only this. So 400, let's say 4200 equations has to be solved. So it is possible in for nowadays computational resources. Okay, so the meshing we do, one purpose of doing meshing is the reducing the number of equations, and how it has to be done I will be covering soon. So and the second purpose of doing meshing is to capture the geometry. For example, this is the 100% geometry. Okay, so if you keep on increasing the number of nodes and element, let's say 3 lines, 4 lines, so it will become then you can actually capture the geometry. The second purpose of doing the meshing is to capture the geometry, which I'm going to discuss. And the third method is the physics. Okay, I'll also cover. I'll talk about the what do you mean by the physics. So before I go to the next, so let me element quality, all the things I'll discuss later on. So here, so my screen is visible. What is visible there?
Yes, it is visible.
What is now visible? Is it showing something?
Yes,
yeah, it's showing.
Revolving.
Okay.
Sphere is not.
Okay. So now see, this is one sphere. I want to show you that how meshing has to be done. Okay, in a sense, how you should capture the geometry, and what is the process, basic process involved in doing proper CFD. Basically, if you use, let's say, Fluent and all the things, they have automated the process of doing the meshing. So many of the time we will even don't see how the mesh look like. We directly go into the result. And many times we face problems of that we are not able to validate our model with the experiment. There is a lot of deviation, and many times we see there is the code is not converging, it's diverging. All those processes are basically related to the mesh generation, which because of this automation process, Fluent, hardly we many of us look into this, how meshing has to be done. So under 1 hour, since I am taking 2 more classes, so I'll be dealing more with this modeling part. So today I will just cover the basics part, how this is done. So this is a geometry of 200 mm diameter. Okay, so one way, let's say if I take a element size of 70, okay, and I select this surface, and if I mesh it, now you see this meshing at the first, the purpose of meshing is to first one is to capture the geometry. Now see, by no means or it is looking like a sphere, though it is a resembles that, but it's not capturing the geometry. Okay, now see, there is these surfaces are flat, this element and these elements are, you can see this highly stressed. I'll cover tomorrow how to check the element quality and what precautions one should take while creating a proper mesh. But today just I'm discussing how. So now this is not the correct mesh. So what we'll do is you can increase the mesh size, or maybe a little bit. If you keep on, let's say, refining, so your number of, if you keep on increasing the number of element, So slowly and slowly it will capture your geometry. In a sense, let's say I increase the number of elements on this, and see, if I increase, then slowly become better and better. So number of element is increasing, so it's capturing my geometry. Okay, and it's not that you can keep on increasing and your result will become 100% accurate. No, it's not like that. Okay, so there is again some limitation in using the more and more element. After some time, let's say if you refinement, you will not see appreciable change in the result. So you should actually, at that time, you should stop the refinement. In a sense, if you use, otherwise you will unnecessarily waste the computational resources. Too much of refinement, and where to refine, I'll also be discussing where we refine the mesh and where we will have a coarse mesh, so that we'll have optimum result. So here in this case, you see the mesh is everywhere is same. Of course, I am not talking about physics, how the flow is there and all things. Maybe I'll come maybe another 10 minutes. I'll talk about the physics more. So here I just wanted to show you the process of increasing the mesh. Okay. Now at this point, one can see that okay, it looks reasonably well. It captures my geometry. So I will stop in a sense. So this is my surface method. This is my, basically initially I had this surface. So inside this there is nothing. If you see, it is just a hollow. इसके नीचे okay, so this is basically I started with the surface. So if you mesh this surface, so it will again be a cell mesh or surface mesh. Okay, so देखो इसके अंदर कुछ नहीं है, ये खाली है. I hope ये दिख रहा होगा वहां पे. It's just a hollow inside. Just in case your objective is to have to see a, let's say, heat transfer inside or flow inside. So the next step you will have to do is to do the volume meshing. Okay, ये इसको बोलते हैं surface mesh. And your volume mesh or a 3D mesh or a tetra mesh or whatever mesh you call it, the quality of that mesh depends upon the your original quality of the surface mesh here. Okay, ये जितना फाइन होगा अकॉर्डिंगली योर जो वॉल्यूम मेश बनेगा वो भी उतना अच्छा होगा. ओके, सो ये हमारा अभी ये बना है डिजिटल सरफेस मेश. एंड टू डू CFD, your first target should be, when you mesh is generated, it has to be a closed surface, irrespective of what kind of CFD you do. You can go to let's say flow over a car, flow over an aeroplane, or a nanofluid, phase change material. When you do a CFD deals with a closed volume. Okay, अगर आपका वॉल्यूम क्लोज नहीं है तो नेक्स्ट स्टेप जो अभी वॉल्यूम मेश करने वाले हैं वो नहीं हो पाएगा. अब देखिए इसको चेक करते हैं. दिस इज वन ऑफ द हाइपर मेश हम यहाँ पे यूज करता हूँ. मैं जनरली इंडस्ट्री में काफी यूज कर रहा था मैं. आपको दूसरा सॉफ्टवेयर यूज करेंगे लेकिन प्रोसेस वही रहता है. इन ए सेंस फर्स्ट यू हैव टू चेक वेदर दिस सरफेस मेश इज क्लोज्ड और नॉट. इन ए सेंस देयर वेरियस वे. सो लेट आई एम चेकिंग दिस find edges. Now you can see at the bottom corner it's saying no edges were found. Selected elements may enclose a volume. ये minimum condition है to proceed for CFD. Please always remember volume mesh होना जरूरी है. So there has to be no error on the on the mesh, or mesh has to be enclosed. So many times, since this is a simple geometry, you will hardly get those kind of errors. But just in case, let's say you are doing a very complicated geometry, okay, let's say interior of a laptop, or doing a lot of components are there, or a building simulation or an aeroplane simulation. So when you import the geometry, some geometry information will be missing, something. So even if you create the surface mesh, it will not be a closed volume. ओके, सो योर फर्स्ट टारगेट इज टू स्टिच, पैचिंग करना है आपको, अदरवाइज वो आपसे नहीं हो पाएगा। देखो जैसे मैं यहाँ पे जैसे मैं एलिमेंट को डिलीट कर दूंगा यहाँ पे, ओके, मान लो इसको मैं एक दो एलिमेंट को मैं डिलीट कर दिया, देखिए वो होल हो गया यहाँ पे ना। अब इसको अगर हम चाहेंगे सीएफडी करने के लिए नहीं होगा, इन ए सेंस ये वॉल्यूम में कर ही नहीं पाएगा। अब बताते हैं आपको, वही प्रोसेस में चेक करता हूँ कि ये कैन बी फाइंड एजेस। तो देखो यहाँ पे बोल रहा है कि 8 फ्री एजेस वेयर फाउंड। ये देखो 2 एलिमेंट को डिलीट कर दिया तो 4 4 8, इसको पहले मुझे ठीक करना पड़ेगा, तभी जाके क्लोज वॉल्यूम होगा। खैर आई विल नॉट गो इनटू दोस डिटेल्स। So now the second step when you do for doing the CFDs, when this volume is closed, is to create a 3D tetramesh, which in this case I'm going to show you. It means basically it will fill up the inside geometry with mesh. Okay, currently it is hollow, so with tetramesh so it is done. Now I'll show you how it look like inside. Okay, so now see, देखो यहाँ पे fill up हो गया अंदर। Okay, the mesh is filled with solid elements, or is basically a finite volume element. From the surface, you see from the surface these elements are little small. Okay, and slowly as you go at the center, it will have a coarse mesh. So the software is doing automatically. And now this then how these elements will be fine near the surface depends upon your original this mesh which you are doing. So if you take a finer element, then you will have a fine element near the surface, which will capture the more boundary layer phenomena near the surface, which I'll discuss now another couple of minutes, how to do all those things. Okay, so this is the basic, and once you will do it, you have a cell element or a surface element, this is the green one, and the 3D mesh. These together will be exported to Fluent. So Fluent need a close bounding surface on the 2D element. This green one is the 2D element, and this 3D element. All these two should be exported to Fluent to do the further analysis. This is a must when you are exporting these two into or for that any matter, any other software like Star CCM or if you export, bring the mesh. So this is a must, these two things. Okay, so before I go to show you how and where to refine the mesh, any question on this? Anyone would like to ask question? Any doubt? So I hope it's fine. So okay. So if there is no further question, so let me.
Sir, someone is asking about software of meshing. Which software it is?
See, this is Altair software, HyperMesh. Okay, if somebody needs trial version, I can arrange. I know from the company, so they will give the student version for 1 year or so. So usually when I take CFD, because of this corona, I am not able to do physically. So I used to teach this 1 week rigorously using this software and Fluent. So students at the end of the course, they are very well versed in handling any complicated design. Anyway, for the time being,
another query is from Mr. Deepak Singh. Sir, is it right by increasing the mesh we can converge to the solution?
Yes and no. Yes is if there has to be an optimum mesh size, number one. So, and for this reason, you see in most of the papers, research papers, we talk about the grid independent test. In a sense, there is a optimum grid level beyond which the result will not be changing much. So after beyond that, there is no point in going on increasing your mesh size. Otherwise, you will have your computational resources will increase, and the this round of error and all things also will compile up, because at each node the error will compile up. So there is a optimum value. It will keep on increasing. Beyond that, it will become counterproductive. So you should not be refining much, and you should not be coarse also, which I am going to discuss it now. I hope it is clear. So grid independent test is a must doing any CFD simulation. Okay, now see any other question or कोई question है? Okay, so now see.
So how to check grid independence?
What about grid independence?
How to check it on the software?
Okay. See, let's say this one. You first start with a very coarse mesh without worrying about the exact result. Perform the simulation and measure whatever parameter you want, for example, lesson number or some losses or velocity. Okay, so that will be not be the optimum, but you will be somewhere 30-40% maybe away from your accurate result. So next time, based upon the first result, so let me show you through. I'll also be showing that one, but I have already certain things in my. Let me go back to. Yeah, see this one. See, this one is geometry. For example, if you want to do the simulation of this, let's say 2D geometry. So here is the inlet. Okay, the fluid will enter from here, and let's say, and it comes out. So this one simple arbitrary design. Now you don't know how. First of all, the number of mesh comes secondary. Now, first of all, how to mesh it? Okay, one way is to just put uniform grid wherever you want. Okay, you don't know how the flow will behave like. Now, if you see if one will see this one, then one may think that fluid will go like this. Okay, it will hit and it will return here. Okay, and again it will go back. Okay, just at the face value, at the design looks like this, and you don't know where to refine the mesh and why to refine the mesh. Grid independent comes secondary, वो बात की बात है. तो first your mesh strategy होना चाहिए, क्या होना चाहिए. Now what I did is I just, without worrying about this this result, I did one simple simulation in the fluid, and see this is how it looked like. So fluid enters here, and there is straight, it goes like this. Okay, without even let's say hitting the right one. Ideally इसको hit करना चाहिए ऐसे, लेकिन ऐसे नहीं हो रहा. The fluid follow the shortest path. Okay, and see here, because of this straight path, this region, ये वाला जो region है, देखो यहाँ पे the fluid is recirculating. Okay, and same thing also is happening here. Okay, so this when we do simulation first for any design or any research, don't worry about the grid independence, that comes secondary. First one is to evolve a strategy how your mesh should look like. So here one can see here the velocity is very small. In this region the velocity is very small. Here also very small. Okay, and these are the region where velocity is very high. So what you should do, if I time permits, I'll also cover this part, how to refine this region. So you refine this region where this velocity, you see, lot of gradient is there first. Okay, and these are the boundary. Near the boundary you can see the velocity is recirculating. So here you also will put high velocity. near the boundary because of the no slip boundary condition, and there is a gradient exists, so we will refine here. Okay, and also refine a region near the. Now once you do refinement, so your mesh is almost fixed in a sense. This is how the mesh should be. So this region should be a coarse mesh. Okay, यहाँ पे coarse mesh होगा. Okay, और ये refined होगा. Okay, now how much will be refined and how much it will be coarse, you will do the grid independence. Then you just fix. So even if you, let's say you this region जहाँ पे flow नहीं है, it doesn't matter whether you put a very fine mesh or very coarse mesh. Okay, because they are not going to affect your result this region. So it is you keep a very coarse mesh here. Don't do much here and keep on changing the refinement around this region where flow is there, maximum flow. And measure the, let's say, whatever you want to measure, let's say any heat transfer quantity or losses or Nusselt number, depending upon your physics, you start monitoring. So first start with a mesh one, it's not much refined. Then keep on refining slowly. This region only. Don't bother about this region. Okay, because as in it will not affect much your result. Okay. Then a stage will come that from successive simulation there will be hardly 2 to 3% variation. Okay. Then you can assume that the mesh which you are taking is now is independent of your grid size. And ideally, when you do research or even do or any design modeling, your results should be independent of grid size. Otherwise, see, then in the research, everybody can claim any result. For you, it can be XYZ. For me, for him, PQR. So that's where the research will not progress. So whenever you present either an experiment, we do also an experiment where we test the repeatability of the result, where results are repeated, can be repeated or not. So in simulation also, we talk about grid independence. So only then it is having some value for me. Otherwise, in the world, everybody will have their own data, which will not be useful to me. So that is what it is called grid independence. So once you achieve a mesh size, you say that yes, XY number of grid is fine. Then you go on changing the physics or boundary condition or whatever you like to do, so all parametric study. Okay, I hope it is become clear now.
Yes, sir. Thank you, sir.
Okay, now see this one. I want to show you how to and where to refine the mesh and why it has to be done. See, this is a pipe. Okay, with some, you can see the color code. It is the inlet. Okay, this one is the inlet, and I have just segregated the surface to this one is the outlet. Remember, when you do CFD, it's better to organize your surfaces into various component, inlet, outlet, and it can be any other surfaces where you want to see the variation or want to apply boundary conditions. Because in Fluent, if I'll export this one, it will be exactly the same name, it will reflect in the Fluent. So there it will be easy. It will be very much easy for me to select the given surfaces like inlet or outlet. I can apply the boundary conditions easily. Okay, and okay, so this one. And outside, see, when you get a pipe, the thickness of the pipe here. So unless we are interested in doing the conjugate heat transfer, conjugate means we see the variations in the solid as well as the fluid. Okay. So if our target is not the conjugate heat transfer, so generally we exclude the thickness part. So you only keep the surfaces where fluid will see or touch the surfaces. So for me in this design, so one is inlet, outlet, and there is one, this is the covering part. Okay. Now many times then what should be the meshing strategy here? Now see, what generally the student do the mistake in doing this. They simply go and let's say they will go and select the surface, okay, and simply mesh with a same size. You can see with this one, the mesh is all everywhere is uniform, okay, almost uniform, because I have selected all the surface with the same mesh size. But this way, this strategy is not the best, because we there in this flow region, from, let's say, from left hand side, from inlet to the outlet, there are regions where flow will not change much, and there is also a region where flow will change drastically. Okay, now from seeing the design, let's say, for left side inlet and outlet, where one will refine the mesh more, or where it is required and why. Can anyone can see the geometry and can tell how meshing should be done?
On the converging section, maybe.
Okay, so there is a section where suddenly there is from inlet to outlet, so the area is changing drastically, and there we need to put more mesh, as simple as that. And other regions we don't need mesh that much, maybe depending upon the physics. If the flow is simply let's say a fluid flow from left to right, then you would like to capture the area where there is, we see more mixing or more reverse flow or something like that, or the gradient of velocity is more. So this is one study. Okay, so we will refine the mesh here. Any other area will look like anybody?
For the boundary layer.
Yes, very good. So apart from this refinement, we will also look about the boundary layer. But where will be the boundary layer? Can anyone say? Okay, where will be the boundary layer? कहाँ पे होगा boundary layer?
So
Near to the walls.
walls.
Yeah. So if there is a boundary, so there will be boundary layer, as simple as that. So near the boundary, so if you are applying a, let's say, no slip boundary condition, where we assume that velocity of fluid is same as the velocity of the wall. So if the wall is static, so fluid will also be static near the boundary. And since a bulk of fluid is moving from the center, so there it will actually automatically develop a huge velocity gradient on the wall. So you need to refine it two places, at least to start with. So here, if the mesh is like this, then you will not get the correct result. Okay. Now, so let me show you how it can be done. So I will abort this mesh refinement. So in the software, it depends upon how you use. So I will select this surface to be a, let's say, element a very fine element size. So I'll say that this surface will always mesh with small size, and rest of the surface, okay, will be with, again, same. You can have a 6 element or 8, depending upon the situation. Okay, so you can find the areas where it is required. Now see, I hope it is visible. आप देखिए यहाँ पे ये जो एरिया है मेरा अब थोड़ा बेटर है. Okay, so I have put a very coarse mesh at the downstream. Of course, agar if you see that there can be the reverse flow is more, if the flow is high, is showing in such a way that it has more, the vortices are forming downstream, so you can also refine further down. But at the time being, you are assuming that the gradient is changing near this region, so I have refined. But again, this is so if you, let's say, do the meshing, so I have some time only left. So the next step, as I said, is the 3D mesh. So the in the meshing processes, first you have to capture the geometry in a proper way. So I have refined here. See, this is only a hollow. Inside you will see there will be nothing actually. If you inlet and outlet को remove कर देंगे, देखिए अंदर कुछ नहीं है यहाँ पे. So it's a hollow geometry. Since there is a flow, so you need to find the fluid properties like pressure, temperature, and velocity. So mesh भी अंदर आपको उसको बोलते हैं volume meshing. This next process comes as a volume meshing. So the inlet and outlet, and with this, this three makes a closed volume. Okay, the same example which I give for sphere. Sphere was a closed. So here also it has to be closed, including all this inlet, outlet. I have just divided the surface into various components. That doesn't matter, but all the components together should make a closed volume. Now, once this is done, we'll go for 3D mesh. Now, in 3D mesh, you will see. Let me show you how it and what is the wrong with this. Even if you do 3D mesh and do CFD, you will not get the correct result. See, in this, my 3D mesh is generated. I'll show you how it look like inside. Now, देखो अंदर में अभी ये कलर दिख रहा है, कुछ कलर और लेना पड़ेगा. हाँ, थोड़ा दिख रहा है. देखिए यहाँ पे मैंने, क्योंकि यहाँ पे रिफाइन किया हुआ था, आप यू कैन सी हियर एलिमेंट्स आर लिटिल बिट स्मॉलर. Okay, because my mesh starts from the exterior and slowly keeps on go and fill the interior, where you see a very coarse mesh here. Okay, here also it happening same finer mesh, but the problem with this mesh is as we discussed, that you need to capture the boundary layer also. If you don't capture that physics, most likely, so one way, other way is to have a very, very fine mesh. Okay, so that the meshes which is generated near the surface will be somehow, it will work like a boundary layer mesh. But again, the number of mesh requirement becomes huge. So we develop a strategy of especially putting the boundary layer mesh, और उसको फ्लुएंट बोलते हैं, शायद इन्फ्लेशन लेयर बोलते हैं, मुझे याद नहीं, इन्फ्लेशन लेयर बोलते हैं. स्टार से हम सॉफ्टवेयर यूज करेंगे तो वहाँ पे प्रिज्म लेयर बोलते हैं, बट द बेसिक कॉन्सेप्ट्स रिमेन द सेम. ओके, सो व्हाट I'll do is I will just delete this one. So this is not the correct way to do the mesh generation. Okay, and see, and this each element, this node, all the equations are there, it is solved. So the and with the 3D mesh, let's say, let me show you. So the number of elements increases drastically. Okay, so I always suggest, so because you can see it is meshes are filled. So for simple geometry, it doesn't matter, but when you when you actually want to do research, I always suggest my student to think of an innovative way to convert your 3D problem into a 2D problem. If you can do this way, by your coming out the new design or a strategy to convert your 3D design into 2D, your 50% of the problem will be solved. In a sense, if you have a 2D mesh, it means one dimension becomes nil. In a sense, only mesh with a couple of thousand of mesh, you can generate a really good result. And it will very fast. Very fast means it will take hardly, depending on the situation, maybe around half an hour or 20 minutes. With one simulation, you can generate a lot of data sets for research and publications. But if you are go for actual design and keep on modeling 3D, then you will get a result. It will keep running for weeks and months, and there will be not much for you to have a do the post processing. Okay, so always be smart when you do your research. I advise my student, and most of my students, they start a research with the 2D. So somehow, and there is no problem in this world where you cannot convert your 3D into 2D. Even if, let's say in companies, what we used to do is you first, even let's say there is company like General Electric, there are a lot of my friends are there. They say that they don't do 3D. First, there is a section, R&D section, where they are given the job to generate a 2D model, do all kind of parametric studies quickly, and then everything is fine-tuned, then they will go for 3D. 1 or 2 simulations they will do to fine check that everything is good. Similarly, here my student, they will come with new practical ideas, and they start doing this geometry and modeling and meshing. But of course, it requires, let's say, a year or so to learn all these things. But I always give them sufficient time to come with a 2D design. And why I do this? I have experience while solving a problem in industry. When I joined in industry in TVS Motor Company, so they were developing actually 3-wheeler. Like you might have seen this 3-wheeler, Bajaj Auto and all those things. So that time in 2006, when I joined, Bajaj and BHU were the market leader. So TVS Motor Company also thought that we will also, since they are already in the 2-wheeler market, so why don't they go also for 3-wheeler? And they started developing. So when I joined, in fact, they started developing this around 2002 or earlier. And when I joined, during testing, the only testing period, so they had a huge problem of engine overheating. Okay, so whenever they will go out for testing and they'll come back in R&D, and moment they open the engine behind, actually we see in 3-wheeler, the engine in the backside, or maybe below the सीट ऑफ द पैसेंजर. अगर पैसेंजर सीट पीछे होता है, उसका पीछे से खुलता है, तो वो पीछे से जब खुलता था ना, इतना गर्म होता था कि ऐसे लगा कि आपका मुंह जल जाएगा. It was so the engine was or the cabin was overheating like anything. So they gave me the problem. So please solve this. You have done PhD or thermal. I think you are still person to solve it. अब मुझे दिया गया, मेरे को भी समझ में नहीं आ रहा है कि इसको प्रॉब्लम कहाँ पे है. Our design and everything looks like Bajaj, बस उनका ओवरहीटिंग हो ही नहीं रहा, हमारा क्यों हो रहा है. तो उसके बाद से धीरे धीरे जब हम लोग टेस्टिंग किए और विद सम डाटा एनालिसिस, हमें लगा कि ये जरूर कुछ इंजन का जो फैन है, नीचे एक फैन भी होता है, एक्चुअली एयर कूल्ड होता है. So like scooter की इंजन ही होती है लेकिन बड़ा होता है, और in the crankshaft the fan will be mounted. So fan will rotate and it will direct the air and to cool the engines. So उन्होंने क्या किया था कि पहले उनकी एक स्कूटी होती थी, स्कूटी पेप, उनका जो फैन को एक्चुअली उन्होंने जस्ट उसका साइज को मल्टीप्लाई करके बड़ा कर दिया, क्योंकि इंजन जो 3-wheeler का था वो बड़ा था, करके फिट करके रन कर रहे थे. तो मैंने सोचा कि ये कुछ फैन का कुछ प्रॉब्लम है, डेटा एनालाइज किया तो फैन का कुछ प्रॉब्लम था. इट वाज नॉट delivering that much air, cold air. So I started modeling the entire engine, the fan and the cabin, and once the model was ready, for one iteration it was taking 1 hour or 2 hours, because model was so heavy, so the system will become very slow. And days were just ऐसे ही चले जा रहा था. My boss was asking क्या हो रहा, बताओ क्या नहीं. So I came with a new idea in a sense. So fan का ही प्रॉब्लम है और इतना 3D करने का मतलब है कि wastage of time. So I came with a new idea to convert this fan design into 2D. So at that time, even nobody can, even today, thinking of a simulation of a 3D fan into a 2D is not that easy. अब इमेजिन करके देखो कि 2D कैसे सिमुलेशन करोगे. So that time I came with a new idea with a 2D simulation, and it was just like a miracle. It was with within 5 or 10 seconds, I used to get one design parameter. So by changing a lot of number of blades, inlet, angle, and all things, in the entire within 2-3 days, I could simulate a lot of, and I found that so there is 30 to 40% mass flow rate was required. So I optimized everything in the software, and I gave them for prototype to test it. And I tell them, sir, कि सर आप 30% मास फ्लो बढ़ जाएगा इसका, इंजन कूलिंग प्रॉब्लम सॉल्व हो जाएगा आपका. देन वी मेक अ प्रोटोटाइप, हमने उसको प्रोटोटाइप बनाया, इंजन में फिट किया, देन वी वर रनिंग एवरीथिंग, and luckily they also measured on the test bed, and my design was bang on the target. मास फ्लो रेट बढ़ गया 30%, जो प्रिडिक्ट किया था सॉफ्टवेयर से बढ़ गया. टेम्परेचर जो मैंने 10 डिग्री टेम्परेचर प्रिडिक्टेड इन द इंजन, वो भी सब, इट वाज ऑलमोस्ट ऑल प्रॉब्लम जो था इंजन का ओवरहीटिंग का इज सॉल्व्ड. And during that time, there are a lot of criticism. How can I, when I was doing the simulation, how can I do such a complex 3D problem into a 2D and all things? But I had some gut feelings that what I'm doing is correct, and I solved that problem. So if you can come into that mode, okay, there is a lot of imagination and oversimplification is required to convert your 3D problem into 2D. And if you can do, I think your 50% life will become easy. Okay, 3D of course is there, and with so much of computational resources available, 3D is also possible. But always make sure that you somehow take your problem to 2D. And see, most of the research problem paper you read, they are mostly in 2D. Okay, so let us come back to this one. So this mesh is not the correct one. Okay, so even though you refine, doesn't matter how you refine, most likely that you will not get the correct result of, let's say, stresses or losses or the pressure losses happening because of this pipe friction and all things. So what you do is you go and create the boundary layer. Let me see how, and again it depends upon the nature of the flow and all things. So when I'm going to I'm telling how to create boundary layer, so I will not be bothering about what is my first layer and all things, just for a demo purpose, that when you do simulation, you should take care of all those things. Okay, so I will delete this. So I'll delete my 3D mesh. Okay, so this is a 3D mesh. So when you export into let's say into Fluent, what it requires is, this is a 3D mesh. Okay, this is the 3D. Inside mesh is filled. Above this, you require this cell element, bounding surface inlet, okay, outlet, and the internal bounding surface, these three. So we need the bounding surface as well as the volume 3D mesh. So after this, you can export into the Fluent, and rest there is process is very easy to select the boundary conditions and the physics. Okay. So now I'm going to show you how to do the boundary layer mesh. So it doesn't matter how refined mesh is yours. Anybody, those who are expert in the CFD, they can say that this is not the correct way of doing the meshing. Okay, so I will delete this. Okay, and I'll just, okay, I think it is. So I will just simply I'll just mesh it arbitrarily with same mesh size. I'm not refining this area. This area can also be refined. Okay, so let me refine that one once more. Till I deleted that mesh. Assign. Okay. Okay, so I have, this is my mesh. Again, this is not the so my next target will be to do the volume meshing with boundary layer mesh. Okay, this is simply a surface, hollow surface mesh. So the process is again same. So in boundary layer mesh, what we do is we define the first layer thickness. There are proper way to calculate depending upon the velocity and fluid air or other property. You can calculate the first layer thickness, and usually it comes about, let's say, 10 to the power -4 but here I will not bother about those things, but for the demonstration. Okay, and the number of layers can be, let's say, initially 5. Okay, and done. And there, then I will select the component with boundary layer. So the component boundary layer will be the surfaces or the wall. Okay, so this is my component, and there is a component without boundary layer. Means what are the other component? We don't want boundary layer in the inlet and outlet, of course. And this together will make a volume mesh. So let me show you. It's just doing the volume mesh. Now see, if you see clearly here, ये दिख रहा है अभी कुछ अपडेट हुआ यहाँ पे?
Yes, sir.
आप देखोगे यहाँ पे तो ये जो near the wall, ये जो this yellow color outside surface is my wall. So there is a fine mesh. Okay, and there is with some geometric progression 1.2 the boundary layer growth. It means the next boundary layer will be 20% higher than the previous one, and slowly it will keep on increasing, and finally at the core it will have a mesh, a coarser mesh. Okay, so you can see here backside also near the wall, यहाँ पे भी throughout the surface ये develop हुआ है. And one is ये आप देखोगे. So let me remove this cell surfaces. तो ये मेरा है वॉल्यूम 3D वाला with a one, and if you let's say want to see the mesh, आप देखेंगे यहाँ पे तो ये देखो लेयर आपको दिख रहा होगा यहाँ पे, ये लेयर्ड मेश है और थोड़ा स्ट्रेच भी है. मैं बताऊंगा इसका बाद में मेश क्वालिटी का क्या इसका इंपॉर्टेंस है. तो ये एवरीवेयर नियर द वॉल ये एक लेयर मेश बन गया है मेरा. ओके, so since near the wall the flow is mostly along the wall, so here mesh can be little bit stressed. Okay, and it will capture the stresses in a better way. Okay, and the rest core is, आप देखो ये दो हमारा ये हमारा mesh का core है, जो 3D mesh का core है ये. ओके, इसके अराउंड है हमारा एक बाउंड लेयर मेश भी बनाते हैं. मेश का देखिए बाउंड लेयर, ये हमारा बाउंड लेयर का कोर है. ओके, एंड अबव दिस ऑफ कोर्स our the three one is inlet, outlet, and the closing volume walls are also there. Okay, if you take this one inlet, outlet, and this mesh, then this is what the fluently. Yes, कोई किसी क्वेश्चन पूछना है? Okay, so and just in case if you are not satisfied with your mesh, you can go and do this first a simple run and see what is the bound layer developed there, and depend upon the other flow and physics condition, you can actually in the second run you can actually optimize your mesh. Of course, there is some quality of mesh which I'll also discuss in the next session. But before I go to the next, anybody is having question? कोई डाउट है, कुछ पूछना है?
Hello, sir. Hello.
हाँ.
Sir, in ANSYS, you can do all that, whatever you told in this hypermesh software.
Yes. See, all these softwares having all the facility almost. So since this is dedicated for mesh generation, they have also some ICM, CFD, and all things modeling. It does the similar job of hypermesh. You can do there also.
Okay, sir. Thank you, sir. Thank you, sir.
But you have to do. It doesn't matter where you do. You may use an OpenForm or Fluent or any software. This is the basic principle which one should follow to get the accurate result. I have seen many publications also that without having a proper mesh and all things, it is done, but that is not the professional way to do the CFD. After this, then
Yes.
rest of the process become very easy. In a sense, you can rely on the results, and you will in this case, and if you want to validate with a particular experiment also, most likely within few percentage error, you can validate. And also,
The problem, then you have to decide what is the boundary layer thickness and all. Then you can put that value. Then you can generate mesh.
yes,
Right,
yes,
sir?
yes, yes. See, the bound layer at the beforehand will not be. You can calculate based upon the certain your
Whatever
Reynolds number.
problem you had.
But again, it's always a hit and trial. Remember, CFD ऐसा नहीं है कि एक बार मेस कर दिए और रिजल्ट आ गया तो फाइनल हो गया. You have to do a lot of hit and trial method. So first time it will not be correct. So go on the second, third, fourth iteration. I think with couple of iteration, and with experience, you'll देख के बोलो कि ये ठीक ठाक है कि सही है कि गलत है. वो सर. So सर और कितना टाइम है? अभी स्टॉप करें कि कुछ और बताएं?
Sir, you take 10 more minutes, 5 to 10 minutes more.
ओके, ठीक है. तो मैं आपको बता रहा हूं कि ये हम लोग ये बाउंड लेयर इतना इंपॉर्टेंट क्यों है. ये आपको एक छोटी सी एग्जांपल से मैं आपको बता रहा हूं. अब देखिए, ये हमारा प्लीज जो हम स्केल एनालिसिस जो बात किए थे, इनफैक्ट आई टीच दिस एंटायर सेमेस्टर स्केल एनालिसिस, but another 5-10 minutes I will just cover to make you understand why this scale analysis is required, and why this bound layer capturing in the CFD is so vital. Now see this one. This is as usual method when there is a plate, okay, and there is a flow coming, so it develops a velocity gradient, okay, like this. Now the purpose of studying the heat transfer and fluid mechanics is only two. Now you will be surprised that with so much of variables and so much of research going on across the world, what is that only two process. One process is when there is a flow in the over a plate or a surface, any surface. So our target is, as an engineer, we would like to know that how much force is required to hold this plate when the fluid comes. So what is the forces acting on this plate? Number one. So this is a part of a fluid or shear stress, whatever you call it, stresses or forces required on the fluid mechanics point of view. On the heat transfer point of view, you would like to, let's say, if the plate temperature and the fluid temperature are different, so there will be heat transfer either from the plate to the fluid or fluid to the plate. So our second objective of studying the heat transfer is to know how much heat flux or heat transfer is occurring between these two. That's all. Anything else is just a derivative of what we study. One can say in a pipe there is what is the pressure drop or anything else. So pressure drop or viscous dissipation, all things is nothing but is just form of some losses which is happening on the surface. So there is only two requirement to calculate the drag force, okay, and the heat transfer rate. Now how it is connected to the boundary layer in theory as well as in the software, why we do so you can see, to calculate the force, drag force, we need, as I said, shear stress into area, integrate. And for the heat transfer rate, you have as heat flux. and you multiply with area and integrate it, you will get the heat flux. Okay, so shear stress by the definition is mu del u by del y, or the gradient in the vertical direction. Okay, and the heat transfer from the surface is happening because of this change in temperature. Now, if you calculate this shear stress, you will be able to calculate the force, which was our main objective of doing this any fluid flow analysis. So shear stress calculation is a must. Okay, and to calculate this Q, how much heat transfer happening from the surface, our main has to be calculated how much heat flux crossing the surface. If these two are calculated, our most of the work is done. But this is not that easy to calculate this shear stress. Why? If you see this shear stress, this shear stress, okay, or I'll not say equal sign, is almost proportional to mu. And this, what is del u? Del u is the change in velocity within boundary layer. So near the surface it is 0, and when you reach the surface here, so this is u infinity, the same velocity which it is actually after a certain distance. So you need to find this distance, this del. So when you write this del u by del y, so basically it corresponds to, this is u infinity minus यहाँ पर u 0 है, क्योंकि velocity यहाँ 0 होगा, यहाँ velocity. So this will be u infinity minus 0. This is his delta y is basically the distance within which there is a gradient. So basically इसको बोलते हैं delta. Okay, so ultimately we get u infinity by delta. So del u by, so this shear stress to calculate force is nothing but this will be u infinity by delta. Now out of these three, you will see that the fluid properties anyway is known, and the free stream condition u infinity anyway is known. What is not known is delta. So if you don't know this boundary layer thickness, this again, this pressure can be, this shear stress can be equated with the pressure, shear stress into area, into blind comes into pressure drop. You can convert into skin friction, all things. This is secondary derivation, but the primary is the shear stress. So if you don't know this boundary layer thickness, you don't know this. If you don't know this, means nothing for your entire fluid mechanism, nothing without this boundary layer. Just imagine the potential theory of the without boundary layer when we discuss. So we cannot, either with theory or using simulation, if you don't know or capture this boundary layer thickness, this we cannot calculate. As simple as that. So if you capture this boundary layer properly, only then you will calculate the shear stress properly, or other quantities like pressure drop, losses, all things, blah blah. You can keep on calculating. Now you understood why this delta is so. I was discussing about boundary layer is so vital. So this is on the fluid mechanics point of view. So if you calculate this one, only this drag force is there. Just imagine this, remove this, that for the time being you don't know. Then you think of any fluid quantity has no relevance. Just imagine that one. Okay, now then how it is related to heat transfer? Boundary layer related to heat transfer. I also will cover how to capture those thermal boundary layer. Now see this heat transfer. See, ultimately whatever heat transfer is happening from the surface to the fluid. So from surface to the fluid, there is some region called conduction layer. There is a must. So first we'll have a conduction near the boundary layer. Conduction will happen, and after that conduction will be taken care of. Fluid heat transfer will be taken by the convection. So conduction will be equal to the convection. Okay. So here you can see. So this HA delta T. So this Q dash or Q heat flux, which you are calculating, okay, is equal to, let's say, H delta T. This has to be equal to the K del T by del Y. This is a conduction near the surface. Now, if you do the scale analysis, this delta T is nothing but this is the delta T. Okay. So this will be the delta T. Okay, same as this one. And this, what is this delta Y? It is the here this the region in which there is boundary layer or the thermal boundary gradient exists. So this will be equal to delta T. Okay, so your heat transfer will become Q dash is equal to HA delta T is equal to K delta T by this. Okay, so this cancel out. Okay, so basically heat transfer H will be equal to, okay, H will be equal to K by delta. So so our ultimate aim of studying heat transfer is to calculate the heat transfer coefficient H, or sometimes we replace this in terms of Nusselt number HL by K, some non-dimensional number. Nusselt number is nothing but this is H L by K. So this L is the characteristic length and K is the property of the fluid, so we will not worry about this. So ultimately, at the end of the heat transfer study, it boils down to calculating the heat transfer coefficient. So heat transfer coefficient you can calculate only when you know the thermal boundary layer thickness. Remember, so if you don't know this, you cannot calculate any form of heat transfer. As simple as that. And this is the reason we put more emphasis on capturing the boundary layer or thermal boundary layer thickness in the heat transfer studies. In most of our situation, let's say air and water, your water Prandtl number is about 7 and air is 1. So there we the thermal boundary layer and hydrodynamic boundary layer are almost same, nearly 1, because this boundary layer thickness is equal to Prandtl number to the power 1/3 or 1 depending on the fluid. So when Prandtl number is small, then you can see for air and water they are same. But again, for different liquid metal or non-metals, it is highly different. So we need to do a proper meshing strategy in the software depending on the problem, so that both you will calculate this del thermal boundary layer, hydrodynamic boundary layer as well as thermal boundary layer. And theoretically, you can see by calculating the order of magnitude. I'm not bothered about this H equal to some constant C1 K by and delta T. So this constant is order of unity. For the time being, you are not worried about that. So scale analysis direct says this small change or the length is very much required to be captured properly. And you can see in most of the when we study this fluid mechanics, mostly we deal with the thermal the calculation of boundary layer, or sometimes we call it momentum thickness or blah blah. Those things I'm not going to detail. Maybe if it permits, next time I will cover more detail of this, how easily you can use scale analysis to solve any kind of fluid problem. Maybe half an hour I'll spend next lecture. So I hope any question this before we stop.
Yeah, any query from participants?
Hello.
Yeah.
Yes.
I'm Ramakrishnan from Chennai, sir.
Yes,
Yeah.
sir.
I just mentioned the question in the chat box. How do you equate that heat transfer rate for both the case conduction convection? Just given the equation just now, HA delta T delta H. How do you equate it? It's not the boundary layers will be changed.
Okay. So let me see within the boundary layer. This is what the system works. Within the boundary layer, the velocities are very, very small.
Oh.
Okay, so there we assume is so near that region only the conduction dominate. Okay, fluid
sir.
conduction. So heat will transfer by the conduction initially near the surface, and once that region is overcome, then comes the convection. The fluid will be heat transfer will dominate by convection. So heat through conduction has to be equal to the convection, otherwise the energy balance will not occur. So and this, I suggest one book, this book by Andrel Bazan, Convection Heat Transfer. Very nice book. The scale and the entire book is based upon heat.
Title of the book, sir. Title of the book, heat transfer.
No, the convection heat transfer by Andrel Bazan. It's available on Flipkart or Amazon with some 300 or 400. Very nice book.
Okay, sir.
Yeah. So I hope it is clear.
As I talking about steady state, am I right, sir?
Yes, yes. Under steady balance, this is what we are calculating. Yes.
Thank you, sir. Thank you.
Any query from other participants? Any query from other participants? No. Thank you, Dr. Singh, for delivering such a nice lecture on the CFD with practical approach. You discussed the fundamental problem in the fluid flow and heat transfer. Thanking you again for giving a valuable time for this nice lecture. So we again meeting your second lecture session is the first and second. We meet tomorrow at the 10:30.
Yeah. Okay.
Yeah. Okay. Thank you. Thank you, Dr. Singh.
Thank you, sir.
Okay.